Hello and welcome to Math 131A, Week 2, Lecture 2. Last time we have proved the arithmetic and geometric mean inequality, usually called the AGM inequality for brevity. Recall that it says that for any real numbers a1 through an positive and n greater or equal than 2, the geometric mean of these numbers, given by the product a1 times a2, etc., times an, taken to the power 1 over n, is bounded from above by the arithmetic mean of these numbers, which is given by the sum a1 plus a2, etc., plus an, and divided by n. And the second topic that we have discussed was the introduction of the symbols plus and minus infinity and the corresponding extended real line consisting of the real numbers plus these two symbols. We have also defined the ordering on this extended real line, and we have defined the meaning of the supremum of a set and the infimum of a set in the situation when they are not necessarily bounded from the corresponding side. So we give meaning to the expressions of the form the supremum of s is equal to infinity, the infimum of s is equal to minus infinity, etc. And here's the plan for today's lecture. We begin by introducing the notion of a sequence of real numbers. This is a crucial notion which forms the basis for our introduction of various notions of continuity in the later parts of this class. But first of all, we begin with the definition of sequences and various basic properties of such definitions, along with examples. And the second topic we are going to discuss today is the notion of a limit of a sequence. Which aims to capture the asymptotic behavior of an infinite sequence of real numbers. And we will start with the definition, the various basic properties of the definition and examples. And we will also demonstrate that in the case a sequence has a limit, then this limit is unique. So we begin with our discussion of sequences. Sequences are a fundamental concept of utmost importance in analysis. Convergent sequences give us a systematic way of talking about particular real numbers, which otherwise might be hard to describe, and they also allow us to understand the asymptotic behavior of infinite sequences of real numbers. We begin with the definition. A sequence in R is a function S from the set of all integers n and z such that n is greater or equal than m to the set of real numbers for some integer m in z. In other words, this means that for every n, an integer, such that n is greater or equal than m, we are given a real number s of n, which corresponds to the image of the function s on the input n. There are several different variants of notation for sequences of real numbers. We will usually denote a sequence S as a sequence Sn, where n varies from m up to infinity. So this is coherent with the notation for summation and for products that we have used before, which alternatively can be written as the set Sn, where n is greater or equal than m, which alternatively can be written as Sm, Sm plus 1, Sm plus 2, etc., where the real number Sn simply represents the image of the function s on the integer n. In the special case, when this particular integer m is equal to 1, we also write that s is equal to the sequence Sn, where n varies over the natural numbers, which equivalently we can write as S1, S2, S3, etc. In some special cases, when the domain of the function s is clear from the context, we might also write that s is equal to Sn without specifying the range over which the parameter n varies explicitly. Let's consider a couple of examples. For the first example, we let the sequence Sn with n varying over the natural numbers be given by Sn equal to 1 over n squared. In other words, the sequence can be presented as the sequence where the first element is 1, the second element is 1 over 2 square, so this is 1/4. The third element is 1 over 3 square, so it's 1/9, 1/16, 1/25, etc. So formally, this sequence is a function with domain equal to the set of natural numbers, whose value at each n is equal to 1 over n squared. Let's consider another example. So we consider the sequence an with an given by -1 to the power n for n greater or equal than 0. In other words, we have a sequence given by an with n varying from 0 to infinity, and an is just the element -1 to the power n. Let's look at a couple of first terms of this sequence. So we have that a0 is equal to 1, a1 is equal to -1 to the power 1, so it's equal to -1, a2 is equal to -1 squared, so it's just 1, etc. In other words, we can present the sequence as 1, -1, 1, -1, 1, -1, etc. So we have an alternation of 1 and -1 along the sequence. Formally, according to our definition, s is a function whose domain is equal to the set 0 together with the set of natural numbers, so 1, 2, 3, etc., and whose set of values is equal to the set of two elements, 1 and -1. It is important to distinguish between the sequence and the set of values of this sequence. So sequences are always denoted using the regular brackets, while the set of values is denoted with angular brackets. In a sequence, many of its elements might be repeated. So for example, the sequence in B consists of only two values, 1 and -1, which are repeated many times. However, a set is just a collection of elements, and it's completely determined by these elements. So in a set notation, there are no repetitions allowed. And with this point of view, there's a big distinction between a sequence and the set of its values. As we see in this example, the sequence itself consists of an infinite collection with 1, -1, 1, -1, etc. repeated infinitely often, while the set of values is just a set of two elements, namely those elements which actually appear somewhere in the sequence, which in this case is just 1 and -1. If you look at the example A, we see that all elements appearing in the sequence are pairwise distinct, and in this case the set of values is also given by the full list of elements appearing anywhere in the sequence. So it consists of 1, 1/4, 1/9, 1/16, etc. So this is distinction to keep in mind. Let's consider some other examples. C, we consider the sequence whose elements are of the form cosine n times pi over 3 for n varying over the natural numbers. The first term of the sequence, S1, is going to be equal to the cosine of 1 times pi over 3, so just pi over 3, which is equal to the cosine of 60 degrees, which is equal to 1/2. And making some further calculations, we can see that the sequence is of the form 1/2. Then we have minus 1/2, we have minus 1, minus 1/2, 1/2 again, and after that 1. These are all distinct numbers. However, after that, the sequence starts repeating. So we have the same block 1/2, minus 1/2, minus 1, minus 1/2, 1/2, 1, etc. So this sequence is periodic, consisting of the block 1/2, minus 1/2, minus 1, minus 1/2, 1/2, 1, repeated infinitely often. The set of values of this sequence is again by definition just the set of all real numbers that appear somewhere in the sequence. So hence, this is the set of all real numbers of the form cosine n times pi over 3, where n is an arbitrary natural number, and we saw that this is of the form 1/2, minus 1/2, minus 1, and 1. So this is the only real numbers appearing on the sequence. There are just 4 of them, even though the sequence itself is infinite. Let's look at another example, D. So we consider the nth element, an, to be the nth root of n. And we let n vary over all natural numbers. Hence, we have the sequence a, which consists of 1, then we have the square root of 2, then we have a cubic root of 3, and the list goes on. Now, calculating these values, we get that this is equal to 1. The next element is going to be 1.41. We only look up to 2 decimal places. The next element is going to be 144. The next element is going to be again 141, ... Then we get 137, etc. So this first fragment illustrates that the elements sometimes go up further in the sequence and sometimes they go down. However, if we go very far in the sequence, one can calculate that, for example, 100 is going to be approximately equal to 1.0471, and the thousandth element of the sequence, 1000, is approximately equal to 1.0069, and as the list goes on, it appears that an gets closer and closer to 1 as n increases. We will see later on how to make it precise. Another example, let's consider a sequence Bn given by 1 plus 1 over n taken to the power n, where we let n vary over the natural numbers. If we perform the calculations for various values of n, we can see that the sequence starts with 2, then we have 2.25, then we have 2.3704, then we have 2.44114, etc. And if we continue this list, one can see that this gets closer and closer. To the number, which can be written as 2, 7, 1, etc. So maybe you can already recognize this number from the first couple of its digits. However, we will see later on that this is a very special number which plays an important role in real analysis. Okay, and finally, let's consider one more example, f. We can define sequences recursively. In this context, recursively means that the nth term of the sequence, fn, is defined in terms of the previous elements of the sequence. So in terms of the elements fk for k less than n. So for example, we can consider the sequence f, which consists of the elements fn, 1, 1, 2, 3, 5, 8, 13, etc. The list goes on, which is defined by the initial conditions. f1 is equal to f2 is equal to 1. And for the later elements of the sequence, they are defined recursively in terms of the previous elements. So we define the element fn plus 2 to be equal to fn plus 1 plus fn. You might recognize it as the Fibonacci sequence. Which arises in many areas of science and other human activities. These examples illustrate several very different behaviors that might occur on a sequence of real numbers. For example, if we draw the real line, one can think about a sequence as marking the elements appearing on it. So we have a 1 somewhere, then we have a 2 somewhere, we have a 3 somewhere, etc. And the sequence goes on. And so in these examples, we saw 3 very different types of behavior. In the first example, we have that the elements of the sequence simply get bigger and bigger, and they never stop growing. So somehow we can say intuitively that the sequence goes to infinity. In another example that we saw, the elements of the sequence only take 2 different values. So they take the values -1 and 1. We have a 1 here, then we have a 2 here, then we have a 3 here, then we have a 4 here, etc. So even though the elements of the sequence don't blow out to infinity, they never seem to start aggregating around a particular real number. And finally, in some other cases, we saw a situation when the elements of a sequence, even though, let's say, keep growing, however, there's some mysterious number, r, which we don't know in advance. However, it seems that the elements of the sequence, as we increase n, start getting closer and closer to some particular real number. So somehow they start accumulating in one very small and smaller region of the real line around this particular real number. So the next thing we want to define is a precise meaning of this behavior. What does it mean for a sequence of numbers to converge to a particular real number? We begin by defining the limit of a sequence and the corresponding notion of convergence to this limit. Definition. Let Sn with n greater or equal than m be a sequence, and let S be a real number. Then we say that this sequence Sn, n greater or equal than m, converges to the real number S if for every epsilon bigger than 0 there exists some natural number n such that the absolute value of the difference Sn minus S is strictly less than epsilon for every natural number n greater or equal than capital N. Now, in the case that Sn converges to S, we symbolically write that S is equal to the limit of Sn as n goes to infinity, which can also be denoted as Sn goes to S. And in this case, we call this real number S the limit of the sequence Sn. Finally, if there is no S, a real number, such that the sequence Sn converges to S, then we say that the sequence Sn diverges. Note the order of quantifiers and the definition of convergence. So we are saying that for every epsilon positive real number, no matter how small, there is always some natural number n depending on epsilon, such that the elements of the sequence Sn, starting with n greater or equal than capital N, are all at the distance at most epsilon from the given real number S, which in that case is the limit of the sequence. So we are not asking that there is some n which works for all epsilon simultaneously, but rather that for each epsilon it's possible to choose some n depending on this epsilon, which guarantees the corresponding condition on the difference. We begin with a couple of basic remarks about properties of limits. So we start with the following proposition. The following are true about arbitrary sequences. The first point is the uniqueness of limits. Given an arbitrary sequence of real numbers, let's say Sn, and two real numbers, S and S prime, if the sequence Sn converges to S and the sequence Sn converges to S prime, then S is necessarily equal to S prime. So if a sequence has a limit, then this limit is unique. And the second item, constant sequences converge to the corresponding constant. Given a sequence Sn, n greater or equal than m, which happens to be a constant sequence, in other words, there exists some real number S such that the nth element of the sequence is equal to this S for all n greater or equal than m, then the sequence Sn converges to S. So this second item should be viewed just as a sanity check with respect to the definition of the limit. If all elements of the sequence are equal, then the limit of the sequence should be that number representing all of these elements. Okay, so our task is now to check both of these properties. Proof. We begin with the first one. So we are given a sequence of real numbers Sn, and we assume that simultaneously Sn converges to S and Sn converges to S prime, where S and S prime are two real numbers. And we start by fixing an arbitrary positive real number epsilon. Now we use the definition of convergence applied to each of these two cases. So the assumption that the sequence Sn converges to S guarantees that there exists a natural number n such that we have that the absolute value of the difference Sn minus S is smaller than epsilon over 2 for all natural numbers n greater or equal than capital N. So we get this by definition of Sn convergent to S applied with respect to epsilon prime equal to epsilon over 2. So note that if epsilon is positive, then epsilon over 2 is also a positive real number, and we know by the definition of convergence that for any positive real number there exists some capital N, a natural number, such that all elements of the sequence starting from that number are within epsilon over 2, or epsilon prime in this case, from the limit S. Okay, so this is guaranteed by the condition Sn converges to S. On the other hand, we also know that Sn converges to S prime. So we can get the same conclusion with respect to S prime. Namely, we know that there exists some natural number n prime such that the absolute value of the difference Sn minus S prime is less than epsilon over 2 for all natural numbers n greater or equal than n prime. Now, given these two inequalities, we would like to choose an index for the elements of the sequence such that starting from it both of these conditions hold simultaneously. So towards this, we let n0 be equal to the maximum of the integers n and n prime. But then, combining these two conditions, we have that for every n greater or equal than n0, we have simultaneously that the absolute value of the difference Sn minus S is less than epsilon over 2, and the absolute value of Sn minus S prime is less than epsilon over 2. Drawing this on the real line, we have two real numbers S and S prime, and we have given a single sequence Sn such that both all elements of the sequence starting from some point onwards start grouping within epsilon over 2 of S and simultaneously within epsilon over 2 of S prime. But these are the same elements, so then the conclusion should be that these two numbers, S and S prime, are necessarily close to each other, right? This is some kind of transitivity principle going on here. So let's make that precise. Our task is to estimate the difference, or rather the absolute value of the difference S minus S prime. So the distance between these two real numbers. Okay? So we have that the absolute value of S minus S prime, which we can write as the absolute value of S minus Sn minus S prime minus Sn, right? So we still get the same expression because these two Sns are going to cancel out. So it's the same. Now for this, we have an upper bound given by the absolute value of the difference Sn minus S plus the absolute value of the difference Sn minus S prime, and this is by the triangle inequality. Apply it with respect to the pair of real numbers, with the first one given by S minus Sn and the second one given by S prime minus Sn. Okay, but now for each of these, we have that this is less than epsilon over 2 plus epsilon over 2, which is just equal to epsilon. Okay, so to summarize what we have demonstrated, we have shown that for any positive real number, epsilon greater than 0, we have that the absolute value of the difference s minus s prime is smaller than epsilon. To rephrase it, we see that for any positive epsilon, the distance between s and s prime is smaller than epsilon. So of course, now we would like to conclude that these two real numbers, s and s prime, must be equal. So this implies that s is equal to s prime. It should be intuitively clear, but let's pause here for a moment and deduce it precisely from the axioms. So assume towards contradiction that they are not equal, so that s is not equal to s prime. Then necessarily the absolute value of the difference s minus s prime is strictly greater than 0, just by the basic properties of the absolute value. Now, since the absolute value of s minus s prime is a positive real number, by the Archimedean property, we know that there exists some natural number m such that 1 over m is less than the number s minus s prime. Okay, so we obtain this, which gives us a contradiction the conclusion that the difference is smaller than any epsilon by taking epsilon to be equal to 1 over m, greater than 0. So we get a contradiction. So the conclusion is that then necessarily s is equal to s prime, and this is what we were trying to prove. So this concludes the proof of part 1. For the second part of the proof, we need to show that a constant sequence converges to the corresponding constant. So we assume that the sequence Sn is given, and we assume that there exists some real number s such that every element of that sequence is equal to this particular fixed real number. Our task is to show that Sn converges to S. Again, we argue just from the definition of convergence and limits. So let epsilon bigger than 0 be an arbitrary real number. We need to find a natural number n greater or equal than m, where m corresponds to the starting index of our sequence. So we need to find the natural number n greater or equal than m such that the absolute value of the difference, Sn minus s, is smaller than epsilon for every element of the sequence indexed by n greater or equal than capital N. Right. But now let's look at this difference, the absolute value of Sn minus s. Since every element Sn is equal to s, this is just the absolute value of the difference s minus s, which is obviously 0, which is obviously smaller than epsilon for all n greater or equal than m. So then we can simply take capital N to be equal to m, or equivalently we can take any integer greater or equal than m. And then the condition on the upper bound for the difference between Sn and S being smaller than epsilon is automatically satisfied. So then, by definition, this tells us that S is indeed the limit of this sequence. Having established these two basic properties of limits of sequences and convergence, let us consider a couple of particular examples. Since in the future we'll have to find limits for many different sequences. We begin with an example of a sequence S given by Sn n greater or equal than 0, where we take the nth element of the sequence to be equal to 1 over the square root of n. And the claim is that the sequence 1 over the square root of n converges to 0. Let's show it arguing from the definition of limit. So we start with an arbitrary positive real epsilon. We need to find a natural number n such that if we look at the difference, or rather the absolute value of the difference of the nth element of the sequence, which in this case is just 1 over the square root of n, and the expected limit, 0, then this has to be smaller than epsilon for every n greater or equal than capital N. So our task is to choose such an n starting with a particular given epsilon. Okay, so we have to define this capital N in terms of epsilon that we are trying to justify. To rephrase it differently, we need to know how large n must be so that the inequality 1 over the square root of n smaller than epsilon is satisfied. Right? This new inequality is equivalent to the previous one simply because 1 over the square root of n is a positive real number, hence the absolute value of its difference with 0 is just the number itself, and so this becomes equivalent to 1 over the square root of n is smaller than epsilon. Now, taking square and rearranging, this is equivalent to the inequality n is greater than 1 over epsilon square. So if we take capital N to be any natural number such that n is greater than 1 over epsilon square, and we know such natural numbers exist by the Archimedean property, then the corresponding inequality is going to be satisfied. So then, for all n greater or equal than n, using monotonicity of the ordering, we have that n is strictly greater than 1 over epsilon square. So rephrasing it, we have that 1 over the square root of n minus 0 is smaller than epsilon. And so we show that the definition of limit is satisfied with respect to the real number 0. So 0 is the limit of the sequence, and the sequence converges to it. Let's consider another sequence that we already defined earlier. So let's look at the sequence minus 1 to the power n, where n varies over the natural numbers greater or equal than 1. So the nth element of the sequence is minus 1 to the power n. Let's think for a second if the sequence converges or not. So let's try to sketch it on the real line. So we have 1, we have minus 1, and now we know that the first element of the sequence is equal to minus 1. Then we have S2 here equal to 1, then we have S3, then we have S4, etc. So this keeps alternating. What do you think? Does it have a limit? Well, no matter what real number we pick, for example, if we pick 1, even though we have elements of the sequence with arbitrary large numbers, which are all actually equal to 1, so arbitrary close to 1, we will always have some other elements of the sequence with indices above any prescribed number, which are equal to minus 1, so they are at a fixed distance from the desired number 1, at the distance at least, at distance 2 in fact. Yeah, and so it seems no matter what real number we pick, we will always have elements of the sequence which are bounded away from this particular real number. So it starts looking like there is no limit, right? So let's make this line of reasoning precise. We argue by contradiction that the sequence diverges. So assume towards contradiction that it doesn't diverge, which taking negation simply means that it converges. If a sequence converges, it means that there exists some real number A such that the sequence minus 1 to the n converges to this particular real number A. But now, if we look again at the real line, no matter where we put this real number A, so it can be here, it can be here, it can be very close to here, or arbitrarily far above. So, but the conclusion that no matter where we put this A, we will always have that either 1 or minus 1 will have distance greater or equal than 1 from A. And this is easy to see from the triangle inequality. So if we have that the distance from 1 minus A is smaller than 1 and the distance from minus 1 to A is smaller than 1, then by the triangle inequality we have that the distance between 1 and minus 1 can be written equivalently as the absolute value of 1 minus A minus minus 1 minus A, since if the a's will cancel out, so we get the original expression 1 minus minus A. But now applying the triangle inequality, we see that this is bounded from above by the absolute value of 1 minus A plus the absolute value of minus 1 minus A. By assumption, we assume towards contradiction that both of them are smaller than 1, so this is smaller than 1 plus 1 equal to 2. On the other hand, this expression is obviously equal to 2, and so we get that 2 is strictly less than 2, which is a contradiction. Okay, so then this tells us that at least one of the corresponding differences, the absolute value of 1 minus A or the absolute value of minus 1 minus A, is necessarily greater or equal than 1. And that's our assertion, that the distance from A to at least one of 1 and minus 1 is at least 1. Okay, so now we use this observation to conclude that the sequence has no limits. So if A is a limit, by the definition of convergence, it must be that for every epsilon real number bigger than 0, there exists some index n such that we have minus 1 to the power n minus a is smaller, strictly less than epsilon, for all indices n greater or equal than n. This must hold for every epsilon. We show that it fails for a particular epsilon. Namely, we can take epsilon to be equal to 1. As by our assumption towards contradiction, the sequence minus 1 to the n converges to a, we know that there exists n such that the corresponding condition holds. So minus 1 to the n minus a is smaller than epsilon for all natural numbers n large enough, so greater or equal than capital N. So substituting the particular epsilon equal to 1, we thus have that minus 1 to the power n minus a is strictly less than 1 for all n greater or equal than n. But in particular, we can take little n to be either even or odd, right? And so in the corresponding case, if it's even, we get that minus 1 to the power n is equal to 1. And if n is odd, we get that minus 1 to the power n is equal to minus 1. So since this must hold for all n, we see that this inequality must hold in both of the cases. So we have that both the absolute value of 1 minus a and the absolute value of 1 plus a have to be smaller than 1. But this is a contradiction because we have just demonstrated earlier that at least one of these two numbers, 1 or minus 1, must be at the distance at greater or equal than 1 from a. So this gives a contradiction, which shows that our initial assumption was incorrect. And so our initial assumption was that the sequence converges to a, where a was an arbitrary real number. So this shows that for no a, the sequence converges to a, hence the sequence diverges. Okay, thank you for your attention. This concludes our lecture for today.